Aleksander is a machine learning researcher, educator, consultant, and author. And in this talk, he's going to be discussing causality in Python.
Thank you so much, Aisha, for the introduction. So the title of the talk is The Causal Toolbox, a Practical Guide to Causality in Python for the Perplexed. Who feels perplexed about causality? Oh, it's not that many people. Okay. Out of the people who are not perplexed about causality, who knows about Perlian framework? Not that much? Okay, so it's 4 people. So the rest of you is somewhere in between. I want to start it with introducing you to this guy. He's a chimp, and his name was Santino. He used to live in Furuvik Zoo in Sweden and died tragically last year, shot by people in a very unfortunate accident. Santino was very typical in certain regards. As he was a male chimp, he was showing dominance. So dominance display is a set of behaviors that male chimps display to show their dominance. And one of those behaviors is stone throwing. So as you can see, there are some people gathering around the island where he was living. He was just throwing stones at those people to show that he's the boss. Well, that's good for the chimp, but not so good for the people, as they can get hurt. So the zoo workers, were hiding the stones from him. And that's also typical. What was not typical about Santino was that even that they searched the island very carefully, and they were convinced they found all the stones that he could use as projectiles, he was still throwing stones. The story became famous thanks to Matthias Oswald, who's a cognitive scientist from the University of Lund. And it turned out that Santino was not only throwing the rocks, but he was also very carefully planning what he will do. And he was planning in advance. Which means that he was collecting the rocks before the zoo was opened, hiding them in a place that he knew that the zoo workers won't look for them there, and then using them when the time was coming. He was also doing something a little more unexpected. He was also collecting the rocks or parts of the concrete parts of the pit around his island during the winter time when the zoo was closed. So he was planning in advance not only a couple of hours, he was able to plan in advance even a couple of months. The chimpanzee appeared consistently to combine deceptive strategies, hiding projectiles and inhibiting display dominance. So he was also behaving very calmly before he started throwing stones, which is not that typical for male chimps. And you can see that he was using different types of stuff, so rocks and also pieces of concrete. The gathering and manufacturing has been observed during the hours before the zoo was opened. And why is this interesting or relevant for this talk today, where we are talking about causality and Python? It's relevant because all those actions that he was able to carry out require something that we would call a world model. They also require something that we tend to call counterfactual reasoning. So counterfactual reasoning is thinking about the future or the past and imagining the outcomes of our actions if we choose one action or another action, and then being able to compare them. So we used to think for many years that prospective memory, planning, counterfactual reasoning are uniquely human. Today we know that chimpanzees are not the only species that can do that. So yeah, so why that's important? For humans, this might be intuitive, thinking about future and thinking about counterfactuals. But when we are trying to translate it into computer programs, we meet a number of challenges on our way. And I want to talk about this a little bit more, but before this, I want to introduce myself briefly. I'm a consultant, educator, and advisor, and a researcher. I'm also author of this book, and I took one copy with me for you. There's more than one person, so. So what I propose is that among the people who will be active today, we will write a simple NumPy program to draw the winner. Is that okay? Okay. So who thinks it's okay? Let's say okay. Okay. Oh, that's powerful. Thank you. For those of you who won't be lucky or don't want to be active, you can learn more about the book by scanning this QR code. I'm also the leader of the Causal Python community. You can learn more about the community and some free resources here. And privately, I love traveling with my wife. And I also enjoy good vegan food. And this is a picture from one of our trips in Costa Rica. And as you can see, there's this big black thing here at the rear part of the motorcycle. And these are all our belongings. So that day, we were traveling from the Caribbean coast to the mountains area. And we checked the weather. And the weather forecast said that most likely there will be some rain on the road. So because we knew that our bags were not waterproof, and we also didn't want all our stuff to get wet, we bought those trash bags, and we put all our belongings in those trash bags. So this is also an example of counterfactual reasoning. And as we said before, for people, there's nothing special about thinking about, hey, it will rain, this is not waterproof, so I need to do this action instead of another action to get to my goal. And our goal here was to keep our clothes dry. So when we think about machines and machine learning, and machines learning patterns or learning stuff in the real world, we often think about the data. And even if not explicitly, we often assume that if there is some variability in the data, in one variable and another variable, we can learn something about the way those variables are linked. So I want to give you an example. I want to start with a question: how to increase the number of non-commercial space launches per year? Around a decade ago, this interesting thing has started that was called the big data revolution. And like everybody was on board, and I was on board as well. And I remember that Google published a paper or a blog post where they said, if we have enough data points, we can answer any question. The idea there was that if we put an expressive enough architecture on a big enough data set, then this architecture will be able to learn all relevant patterns in the data. So one data-driven answer to this question that you see on the screen is to increase the number of PhDs in sociology in the US. Is that a good answer?
Nope. Let's get another Elon Musk.
I count this as activity. What's your name?
Elaine.
Elaine? Thank you.
Thank you.
Why did I propose this answer? Because the data shows that there's a very strong relationship between the number of non-commercial space launches and sociology doctorates in the US. You can see that the correlation is, well, It's pretty strong. And it holds for over a decade. So in the community, in the data community, you will meet people sometimes who will tell you, of course, correlation is not causation. But if we observe consistent correlations over time, this is an indicator that maybe there is causation there. As you can see here, and I assume that we agree here that the answer, that the number of sociology PhDs causes number of non-commercial space launches is not a good answer. Then you can see that this is not necessarily the case. So traditional machine learning, and I would say traditional associative machine learning. We'll talk about why associative. We'll talk about this in a second. It's great for prediction under the assumption that the future is like the past. So we say the joint distribution that we used for the training won't change at test time. It often changes. And some people would propose that, for instance, using like automated ML ops would be a solution to this problem. It might be sometimes. But in most cases, this traditional associative way of doing machine learning is insufficient for decision making. Going back to the example of our journey in Costa Rica, our trip in Costa Rica, well, predicting that it will rain is not enough to make a decision what to do. And we'll see a more precise example in a second. All that said, traditional associative machine learning can be very helpful as a component of a larger decision-making system or a causal system. In causal modeling, or why we even think about causal modeling, is because we want to understand what will happen if we make a certain action in the world, or as we sometimes call it, we intervene in the world. So you can imagine, what's your name?
Suri.
Suri? We can imagine that Suri has a headache today. I hope it's not true. And somebody comes to Suri and gives her a painkiller. She takes it, and 1 hour from now, her headache is gone. We can ask a question now, was the painkiller the cause of Suri's headache going away? And one intuitive answer is that yes, because we know something about painkillers, we know something about the time it takes for them to work. But it's not necessarily the case, right? Maybe she's sensitive to atmospheric pressure, and the pressure has changed. Or maybe there's something else. Maybe this was just a placebo effect. So you were just convinced that it will work, and it worked this way. So traditional associative machine learning cannot help us answer those questions. In particular, those questions might have a form like this. If we do X, will it change Y? Or will Y be larger if we do X, or if we abstain from doing it? And you might think that there's a problem with this. What do you think could be a problem with all of this? Trying to answer those questions. Yes?
Confounding variables, confounding factors.
Confounding
You can't
factors.
just control X without understanding what A, B, and C are doing.
Mm-hmm. What's your name?
Sep?
Sep?
Yes.
Yeah, so confounding variables. So there might be some variables that are changing the X and changing Y. But if we are able to control X, and we know how to control it, and why we control it, and when we control it, for instance, if we randomize X, then we can get rid of those confounding variables. But that was a very good answer. Thank you. There's another problem with this, that we can never observe all potential outcomes. So Suri cannot take the pill and not take the pill at the same time. right? And this is called the fundamental problem of causal inference, as Paul Holland called it in 1986. And this means for us that we need to somehow simulate at least one of the outcomes. So we said a little bit about causality, but we haven't defined it. So what actually is causality? This is one of the definitions that I found on the internet. It comes from Wikipedia, in particular from the article that discusses causality in the context of physics. Is it a good definition?
Consequence. Something is the consequence of something else.
Mm-hmm.
Is it the same as this?
Probably. So do you think it's a good definition or?
I have a feeling that you don't think so.
But that's not the question.
But it seems to, it sounds right.
It sounds right.
Yes.
Okay. Why does it sound right?
Because it has the words relationship and causes and effects in it.
Mm-hmm. Great. Thank you. Okay, we have some more voices here.
It has the limitation for our purposes that it's bidirectional, which is okay in physics because nearly all the fundamental equations are time symmetric.
Mm-hmm.
And that is actually one of the fundamental problems at the basis of physics, is how do you choose the direction for time.
So if I understand you correctly, you're saying that there is no indication of directionality here in this definition. What's your name?
Kevin.
Teddy?
Kevin.
Kevin. Thank you, Kevin. That's a good one. So we could argue that if somebody says causes and effects, then we would say that causes are before effects, right? But it's not explicitly stated here.
No.
And this leads us to another problem with this definition, but we have another voice there.
Let's say, what about like second law of thermodynamics, or like the motion towards entropy, not come off a table and it breaks, you're increasing entropy, that's only one directional. And
Yeah.
that would be an example of actual cause, where it's not symmetrical.
Yes. So what's your name?
Josh.
Josh? Thank you, Josh. So Josh said to those of you who maybe were not able to catch this, that, hey, what's about the second law of thermodynamics? And there is this inherent notion of entropy increasing in one direction. That's a very good intuition as well. Okay, we could also say that this definition is circular, right? So it says that causality is defined here using causes. And causes, well, we still don't know what it is. So maybe this definition doesn't tell us that much. So can we do better? Causality is a topic that was discussed in virtually every culture in the world. If you look through ancient Chinese texts, you will find people thinking about causality. You will find it in Muslim texts. You will find it in Jewish texts. And virtually any other culture in the world that left some textual heritage, you will find people talking about causality. Of course, also Aristotle and all Greek philosophy was vividly interested in this topic. The problem with the definitions that we can find in those texts, often religious or early philosophical texts, are that these definitions are not very actionable. So maybe people captured some interesting intuitions there. And I think it's worth to study those texts, because sometimes you can learn very interesting things about how people in different cultures perceived how we can act in the world and what does it mean, but it's not really actionable. So the definition that I want to propose for today comes from Judea Pearl, and it says, A is a cause of B if B listens to A. This is a very simple definition. We can call it interventional in a sense that we talk about taking action or doing an intervention in the world and observing the outcome. listens to means that we expect that if we change something in A, something in B will also change. And as you can see, this already is somehow conceptually different from this idea of associations that we discussed in the beginning. Because here we talk about the action. And we'll see in a second why this is important. So this is a so-called the so-called ladder of causation that comes from also from Judea Pearl's works. It has 3 rungs. We can think about this ladder of causation as a useful metaphor that helps us grasp certain concepts related to causality more in an intuitive sense. But it's also a formal system that can be defined precisely in measure-theoretic way and topological way. We won't discuss it today because we don't have time. But we will discuss them more intuitively. So the first rung is association, and each rung has an action that is related to this rung. So association is related to observing, looking at the world, and seeing that maybe some things in the world are changing together. Then we have interventions, which is acting in the world, and seeing what happens if we change something. And finally, we have counterfactuals that we discussed briefly in the beginning. And counterfactuals, or counterfactual reasoning, is related to imagining. So we imagine this alternative world, for instance, the alternative world where you did not take the pill, and we are comparing the outcomes in this alternative world to the outcomes that we observe today. And this might sound like a scientific voodoo, because what is it, just dreaming about something? But it turns out that counterfactuals have a precise formal definition, or a set of formal definitions. So we can talk about each of the ranks here in a mathematically rigorous way. And so the apparatus that mathematical apparatus that we will use for each ranks, here we will just use correlations or some generalizations of correlation. That could be information theoretic measures, very, very general, but they still look at associations between 2 or more variables. Then at the interventional level, we will use, we'll start using stuff like do calculus, or we'll start using stuff like structural causal models, and so on and so on. And counterfactuals, we will only use structural causal models that will need to have the richest representations of all of this. So another way to think about this is that for associations, the data itself is sufficient. For interventional distributions, we need some external information that is beyond the data. Now, sometimes we will be able to make interventional conclusions from observational data. But we'll need to make certain assumptions. And finally, for counterfactuals, we will need the richest information. So we will also need some external information, but the representation will need to be richer than in the case of interventions. Okay, so how can we translate all those beautiful abstract ideas into something practical? We started with this idea of the definition of causality from Judea Pearl. A is a cause of B if B listens to A. And Pearlian framework comes with a set of tools that we can use to translate these mathematical formalisms into something more practical. One of the tools are graphs. They look very simple. We often use directed acyclic graphs, or DAGs. But most of the things that we will discuss today can be generalized to either cyclic or not fully directed cases as well. So let's see a quick example how this may work, how this might work, and how we would be able to translate between those graphical representations and their properties and statistical properties of the data. So I want us to imagine a fire alarm. And we have only 3 variables in this system. There is alarm, there is smoke, and there is fire. And we assume that the alarm is based on a smoke particle detector, which means that it won't react to temperature changes, or, I don't know, fire itself. It will only react to fire through the smoke. A system like this could be represented by a graph like this. We have fire, which causes smoke, and smoke causes alarm. We can assume it's deterministic, and we can say there is some stochastic noise in the system as well. Let's talk about deterministic just for the case of simplicity, for the sake of simplicity. And now, what is interesting about this graph? Nothing is also an answer. Yes? Yeah, you after
Fire
first.
isn't directly connected to alarm.
The
Fire is not directly connected to alarm.
that the fire is not directly connected to alarm. Yeah. I think this is a very interesting property. Why is that interesting?
Well, because I guess where I think where it's going is that the smoke is causing the alarm to go up, not the fire.
Mm-hmm. And, okay.
We call it a fire alarm. It should be like a smoke alarm.
Not my choice. What's your name?
Susha.
Susha?
For me, it's just I opened my oven alarm. So.
Yeah. Yeah.
The other thing that's interesting is from that graph, you can make the inference from the alarm that there is a fire.
Again?
To make an inference from the alarm, if the alarm goes off, there is a fire.
Yeah.
Because there is a direct causal relationship.
Unless something
along the
else
chain.
caused the smoke, though.
Yeah, and that's both are very good intuitions. Thank you. So one thing that is, I think we already implicitly said this here and here. One thing that's very interesting here is that if we look at smoke, if we observe smoke, the alarm and fire become independent. Which means that if there's smoke and the alarm goes off, there's nothing. The fire it's independent of fire. Okay? If we think about this in the terms of regression, you will see this. So all information that, in other words, I will give you another perspective on this. All information from fire goes through smoke. So if we know that there's smoke, the fact if there is a fire won't change anything for the alarm. Maybe you will just open the oven. What's your name?
Lucas.
And this property translates to any system that has this structure. And this structure is called a chain, which means that A and C will become independent given B. Now, we could change some arrows here to get another structure. For instance, this one, a fork. What will happen with A and C if we control for B? Yes?
A and C, they will be like correlated, but they are like independent.
So you said they will be correlated, but independent. In which case?
Yeah. So they will have a correlated outcome, but they don't cause each other.
Yes. And if we control for B, or if we don't control for B? So you said they will be correlated, but they don't cause each other, which is true because we see that the arrows go in the other direction. What's your name?
Oliver.
Oliver.
Would it be that if they would appear correlated until you control for B, and then it should in principle then be?
That's a very good answer. What's your name?
Scott.
Scott. Yes, so as you can see, B is a common cause of A and C, which means that there is some change in A and change in C that comes from B. And those changes are correlated because they come from one thing. Thank you. So if we exclude this, or we partial it out, for instance, in the regression framework, there will be no common variability left in A and C. Now we have another structure that is called a collider. What would happen with A and C? So what is the relationship between A and C if we don't control for B, and what will happen if we control for B? Yes?
If you control for it, they become correlated.
If we control for B, they will become correlated. And what if we don't control?
Then they shouldn't be correlated.
They shouldn't be correlated. What's your name? Danny?
Dan. D-A-N.
Dan. Thank you, Dan. And that's the correct answer. And this is a very important fact because you can see now that if we run conditional dependence or conditional independence tests, we cannot distinguish between those two. Of course, we are talking about a situation where we don't know the arrows, the direction of the arrows. But we can distinguish between those two, forks and chains, and colliders. Because A and C will behave differently if we control for B versus do not control for B. Then they will behave for fork and chain. And this also translates to statistical properties. So you can see for chains, A is not a significant, so C is the outcome here in those regressions, and A and B are predictors. If we control for B in the chain, B is a significant predictor of C, but A is not. The same is the case for fork. A significant predictor, B, not significant A. But for collider, although A and C are not causally related, A and C are significantly related. And this has tremendous impact on the outcome of any statistical model in terms of feature selection. So we know that we have automated feature selection algorithms that we use in machine learning traditionally. They work very well. And again, this is one of the reasons why this feature selection will only work well, or the models with these feature selections will only work well in the IID setting. Because if we change something in the underlying joint distribution, then the model will have predictors in it that are not causally related to the outcome. And so the distribution will not map to what is happening in the real world. And so if you want to learn more about this particular aspect, there's a great paper on this by Carlos Cinelli, Andrew Forney, and Julia Pearl, just from last year. And one of the effects why this is important, or one of the reasons why this is important, is this. This comes from my book, and I will say this very briefly. So here, if we control for a variable, one variable in the model, we might either get a result that drag A is better for, that drag B is better for everyone, but it's worse for males and females. But if we change the feature selection in the model, the drug becomes bad for everybody, but it becomes good for males and for females. And this is so-called Simpson's paradox. And this means that statistical control, without thinking about the causal structure behind it, the data generating process, as we call it sometimes, will lead to the outcomes that are not representative of reality. And this is something we recently hear about a lot in the context of large language models. When we ask those models about factual information, we get complete, very plausibly sounding, but complete gibberish. But it turns out that we don't need a very complex architecture like LLMs. Linear regression is enough. So we can get statistically significant results in linear regression with very, very low uncertainty that completely do not translate to reality. And if you want to learn more about this, you can see this is the podcast that we released just 2 days ago. It's called Causal Bandits, and we talk with some great researchers and practitioners in the field. You can check it here. OK, we have very little time, so we'll have to run very quickly now. The 4 steps of causal inference. So how we translate those ideas into practice? Well, first we need to model the problem, and this is something that is different from traditional machine learning, because we need to say something about the data generating process. Then we are finding the estimand. What is an estimand?
Something you use to estimate? Something you use to estimate something?
Something, yes. Something we use to estimate something, which is basically finding a quantity that we want to estimate. So in machine learning, we'll just say, hey, we are interested in the expected value of y given x, a set of predictors. But here, if you want to translate causal queries into statistical language, we will have to very carefully construct this expression, this conditional expression, to do it. So this is the estimand, and there are many estimands. And they encode our causal model of the world, our belief. And then we are computing estimates. And finally, we are validating the model. So here we have some code, which we will go through very briefly. And we'll use a package that is called doy. And then at the end of this notebook, you will also have another package that is called econml. So these are some helper functions. Here we are generating some data. And then you can see that we are constructing this graph. And the graph is representing the data generating process. Here we construct it manually, but we don't have to always construct it manually. We can try to automate it. We are not yet in a place where we can completely automate it from observational data, but we can partially automate it. And then there is a class in doy called causal model that takes the data, information about which variable is the treatment, which variable is the outcome, and it also takes this extra statistical information, which is the graph, which represents our belief regarding the data generating process. We can view a model like this. So here we can see that we have one unobserved confounder here. We cannot observe this variable. We know it's there, but we cannot observe it. We have x that is our treatment, y that is our outcome, and we have this variable in the middle, which is z. It's a mediator. Yeah?
You get bigger.
This?
Yeah.
I'll try. Is that OK? And so now there's a set. We mentioned briefly do calculus in the beginning, which is a set of rules, how to translate causal queries into statistical ones. And doy can find for us automatically the way how to do this translation. Not in every case, but in some cases. We use this identify effect function on the model object. And you can see that it only currently supports 3 types of estimates. First is backdoor, and it says no such variables found. Second is IV, which stands for instrumental variable, and also not found. But luckily, it found the estimate, the front door estimate. There's an expression, a symbolic expression. It also lists the assumptions. And then when we have this estimate, we found this, we can use the estimator to estimate the effect. And in our data, I won't show you because we don't have too much time, the true effect was minus 0.42. So let's see how well it did. Minus 0.41, rounding up. So this is pretty close. If we would run a traditional machine learning model on this and try to estimate this effect and then change something in the underlying distribution, this model would go south very, very quickly. And finally, we have this idea of refutation tests, which is I would say, it's a weak way of validating the model. In particular, the assumptions part of the model, the assumptions about the data generating process. Why I say it's weak, because it changes something either in the model or in the data and checks if the outputs are as expected. So some methods of refutation tests we would expect that the effect is changed. For some other methods, we'll expect that it's not changed. So here, for instance, we just take a subset refuter. So we take a subset of the data, we rerun the models, it runs a lot of iterations in the background, and it gives us the result. The new effect is minus 0.41, and p-value is very high, which says it's insignificant, which in this case says that there are no violations in our model that would lead for this particular test to fail. So this is just a very weak way of validating the models. And then we have also something, so far we're talking about the general effect. Like when we run an RCT, a randomized controlled trial, we will try to estimate what is an average effect of something on certain population. But sometimes we might be interested in effect for a particular subgroup of people. And so you can check it here in this code, and that would be for you.